Unit 7.1, Thin-Walled Pressure Vessels. The course outcome for this unit is to apply your knowledge of stress distributions to calculate stresses in structures under combined loading. In this lesson, we will focus on the outcome to calculate stresses in thin-walled pressure vessels. So what's a thin-walled pressure vessel? Here is a commonly seen pressure vessel. It is a propane tank. It is a cylindrical vessel with two spherical end caps. Here's another example of a cylindrical pressure vessel, much larger than the previous example. A fireman is not a pressure vessel, but the hose they are using behaves in some ways like a cylindrical pressure vessel. Here is a segment of a water main that was dug up from below the ground after being in operation for a few decades. End caps were put on each end, and the pipe was filled with water. And the water was pressurized until the pipe failed. And here you can see the crack in the pipe. It's a longitudinal crack. It's in the direction of the longitudinal axis of the pipe. There's something important about the direction of the crack, and we will talk about that as we go along. So let's suppose we have a pressure vessel with an internal pressure, we'll just say is P. If we take a ring around the pressure vessel, slice through, theoretically, cut out a hoop from the cylindrical pressure vessel, and we'll say it has a width of dx. And here's that hoop shown. Here's the internal pressure acting in all directions. And if we take that hoop and cut it in half and look at it from the side, it will have a half circle with a diameter of 2r, where r is the radius. And it has some wall thickness t. From the opposite half of this circle, we have an internal pressure P acting on this cut surface as shown. And the walls of the pressure vessel are resisting that pressure with a force. And we'll say each wall, top and bottom, takes half the force. Now if we sum our forces in the x direction, we will take our pressure, and to convert pressure to a force, we need to multiply it by an area. So we'll multiply it by this height, 2r, times the width of this ring. That's the width into the screen. That's dx. We'll subtract off these two forces and set that equal to 0. And we can solve for the force. It is equal to 2 times p, the internal pressure, times the radius, times dx, the thickness of our hoop. We'll call that equation 1. Now let's think about the area of the pressure vessel wall along this cut. Well, we have two sections of wall. They have a thickness of t and a width dx. So the total area that these two forces are acting over is 2 times t times dx. We'll call that equation 2. And if we substitute equations 1 and 2 into this expression where normal stress is equal to the force divided by the area, we get that normal stress is equal to P times R over T, where P is the internal pressure, R is the radius, T is the wall thickness. Keep in mind the radius is the internal radius of the cylinder. And we call this stress, we'll call it sigma 1, and it is called the hoop stress, or the circumferential stress. That's the stress that this hoop of material is feeling when the pressure inside tries to enlarge it. It will feel a tension, which is a normal stress. And we can think of the cylinder just being a bunch of hoops placed side by side. Now let's consider again our pressure vessel, which has an internal pressure of P. And this time let's make a theoretical cut as shown and evaluate the stress on this surface. Now there's an internal pressure, P, and it's acting over the surface here. That's the pressure from the piece that we cut off. That's the pressure it's exerting on the piece that remains. And let's say there's an internal radius of r. We can calculate what the resultant pressure force is by taking this internal pressure P and multiplying it by the cross-sectional area of our cylinder. So it'll be P times pi times r squared, where pi r squared is the cross-sectional area of the cylinder. The wall of the cylinder will be resisting that internal pressure, and there'll be a stress, we'll call it sigma 2, induced in the wall. And we can find the resultant resisting force of the tank wall. That'll just be equal to this stress, sigma 2, times the area of the tank wall. So the force is equal to sigma 2 times area, and the area is the perimeter, 2 pi r, times the thickness, t. And we can set this resultant resisting force equal to the resultant pressure force. And let's solve for sigma 2. We get sigma 2 is equal to PR over 2t. And this is called the axial stress, or the longitudinal stress, because it acts in the direction of the longitudinal axis. So if we have a pressure vessel, and if we look at just one small element of the wall thickness on this pressure vessel, it will have a stress acting in the hoop or circumferential direction equal to sigma 1, which is PR over t. And in the longitudinal direction, we will have a normal stress, also a tension stress, sigma 2, which is equal to PR over 2t. So we see that the hoop stress is twice as large as the longitudinal stress. This explains why the pipe that I showed previously fractured in the longitudinal direction. That's because the hoop stress in this direction was the greater stress, and so the rigid pipe material cracked perpendicular to the tensile stress direction. So the equations sigma 1 and sigma 2, which we just developed, apply to cylindrical pressure vessels. Now let's talk about spherical pressure vessels. Here's an example, some spherical pressure vessels. Here is another. Let's look a little more closely at one of these spherical vessels. If we were to make a section through it, through a circumference, draw a free body diagram, and let's say this spherical pressure vessel has a radius, internal radius, r, and a wall thickness, t. There is a pressure acting on this half section, and that pressure comes from the opposite side of the sphere that we have cut off. And that pressure acts over the cross-sectional area of the sphere. This pressure causes a resisting stress to occur in the perimeter of the tank wall. And these same conditions gave us the equation for sigma 2 in a cylindrical pressure vessel, and sigma 2 is also the expression for the stress in the wall of a spherical pressure vessel. And sigma 2 will exist no matter how you cut your circumference through the sphere, which means that the sphere only feels the stress of sigma 2, which is PR over 2t. This means that the maximum wall stress in a spherical pressure vessel is half as much as the maximum wall stress in a cylindrical pressure vessel. So these equations that we developed apply to thin-walled pressure vessels. And to be thin-walled, this must be true, which is that the ratio of r, the internal radius, divided by the thickness, must be greater than or equal to 10. If it is less than 10, then the equations are less accurate. And for thin-walled pressure vessels, we can neglect the radial stress. And we're done.